So I'm going to set these up and tell you why I'm doing what I'm doing. So if you look, in each of these little graduated cylinders, I set up a piece of basically chromatographic paper. It's really just filter paper cut into a strip. And then I have a line that marked in pencil, and then I put an ink spot on there. That ink spot is a mixture of different chemical dyes that you find in food coloring. So what I'm going to do is I'm going to try to separate these dyes by thin film chromatography or just paper chromatography. And what I'm going to do with that is I'm going to, come on, here you go. I'm going to show you how intermolecular forces plays a role in this. Because as it turns out, the surface of the paper has some polarity to it because it's made out of cellulose, which is kind of a long polymer chain of sugar molecules with a lot of OH groups. But the liquids are going to basically wick their way up through capillary action. By the way, I didn't show you this yesterday. This is just a standard paper towel, and I folded it up. In one beaker I had put water, in the other beaker it was totally dry. And overnight it sat, and if you look now, the water levels are about the same. That's capillary action. That's how wetting and things like paper towels are absorbent, because what happens is there's all these little tiny gaps in the fibers of the paper towel that the water molecules can literally travel against gravity, and they end up on the other side. What? Yeah, that's part of how they pull water into their root systems. So the reason I wanted to show you this, I wanted to show you that the liquid will wick up, or literally capillary its way through the fibers, because that's how this little chromatography setup is going to work. Now, if you look on the paper I just gave you, if you flip it to the back, you'll see the structures of the dye molecules. Now, these are pretty complicated looking things, right? And I put on the link so you can get a better look at them, kind of nicer colored pictures here. But let me kind of look at these with you for a moment, and I'll zoom into them. These are the actual dyes that are in the mixture. And what I want you to notice is they're really complex. All these black lines and corners represent carbon and hydrogen, so it's a lot of hydrocarbon backbone. But what's really of interest is there are these kind of ionic and polar pieces on these dyes as well. And that influences their ability to attract, through intermolecular forces, different molecules. So this is the blue dye. You'll notice it has 1, 2, 3 different ionic positions and a couple of rather polar positions as well. It's got, like, in its whole structure, like 5 sites where it can really strongly interact with charged particles. When we look at the red dye, again, is mostly a carbon and hydrogen backbone, but it's got a couple ionic spots and a few polar spots as well. And then finally, the yellow dye in the mix looks very similar to the red one. 1, 2 ionic spots and a bunch of polar spots throughout. So what's tricky about this is to really assign this as being polar or nonpolar. It's not a yes-no question. It's a question of degree. And if you look at these structures, they're all somewhat similar, especially the red and the yellow. You can hardly tell them apart. They look very similar. So it's going to be hardest to separate those two, I think. The blue one is different enough where I think we'll get reasonable separation. So what we're going to now look at is how do different solvents take that spot of dye that's sitting on here and separate it based on how the liquid that I'm going to pour in rises up. So I'm going to put different levels of polar liquids into this, into each one. So if you look at the bottom, that table has all the different solvents that I'm going to use. So I'm just going to do them in that order. And then while it's running, I'm going to talk to you about the theory of how this technique works. And then we should also have some time to go over yesterday's thing as well. Okay, yeah. Oh yeah. Wow, that did not work at all like I planned. Okay, so what's my first solvent? Can you You guys tell me the one on the table?
Hexane.
Hexane. So I'm going to put equal amounts of each, so everything's as consistent as possible. So I'm going to pull out the paper with the stain on it, which is a mixture of dyes. I'm going to put about 5 milliliters of hexane. So what would you say about hexane in terms of polarity? Why do you say it's very nonpolar? You're right.
It's basically a hydrocarbon.
Yeah, it's a purely hydrocarbons. So here's my hexane. I'm going to slide this in, and then the liquid's going to run up, and we're going to see what kind of separation we get.
It's going to rise.
The liquid's going to rise, and it's going to encounter the dye, right? And as it goes, you ever do this thing where you spill paper, like water on one of your notebook papers, and you see the ink smears?
Mm-hmm.
That's what I'm doing here. But if I do this right, I'll get it so it separates all the colors. There's 3 different dyes I'm trying to separate. So that's the hexane. What's next on the list?
Ethyl acetate.
Ethyl acetate. That's this one. So this one, would you say has some polarity?
Yeah.
By its structure? Okay, again, 5 milliliters or so. All right, there's our ethyl acetate. What's next on the list?
Acetone.
Acetone.
Yeah.
Acetone has some polarity, doesn't it?
Yeah.
I'll start there.
Yo, that's not
All right.
Yo, Jody. That's not you.
I need somebody have a stopwatch on their.
I'll take out my stopwatch.
Somebody start a stopwatch while I'm doing this, please.
Do we just start it right now?
Yeah.
Just started it.
I know he's got like a coach street.
Listen up. What's next?
It is ethanol.
Ethanol?
Yo, he's got like the
Ethanol is next. Again, about 5 mils of liquid. What am I doing? Making these? Because I'm testing paper chromatography as a way to also explain a little bit more about intermolecular forces. So this is an actual lab technique that we can use to separate mixtures, and I'm trying to show the difference between using different solvents, and then we're going to try to explain that in terms of intermolecular force, like why some separated better than others. What's next?
Water.
It's water, right?
Water.
Water is very polar, as I recall. Yeah, a little bit of water. Whoops, that's too much water. That's 5, that's beautiful. All right, water.
And then salt water.
And then salt water. Why do you think I made salt water?
It's ion.
Oh, it's ionic.
Doesn't salt water add more polarity because there's salt that has ions?
No, it's a trick question.
No, it's not it.
Oh.
That's actually right. All right. So now you guys are going to be able to watch these.
I'm not doing it.
It's going to take some time. That's why I'm doing this first, so that they can run while we're talking about what's going on.
Let me know when I should stop the timer.
I will. I mean, I want this to run all for about maybe 25 minutes. So if you could just keep track.
Oh, one's already. I think water's already automatic.
Okay.
Wait, how does that work?
The question is, how does it rise? So, capillary action. Remember the little tubes I showed yesterday? And this thing I just showed with the paper towels? What's happening with capillary action is when you have a very narrow opening and the liquid molecules have strong adhesion to the surface, and you put some liquid in there, instead of just staying at the level of the glass, or whatever the tube is, because there's an attraction between the liquid molecules and the glass, they just randomly moving around, they kind of move along the glass, and they rise up against gravity because they stick to the side. That's capillary action. Now, the thinner the tube, the higher it can rise. And when you have something like a piece of paper, if you could magnify it, you would see lots what look like ropes intertwined, but those are molecular strands. And so there's lots of little spaces in between that act like little capillary tubes where the water molecules or whatever solvent molecules can cling and then keep just randomly sliding around and climbing. It's kind of like a ladder, you know? And so they're just randomly meandering their way up. That's why it's climbing up. Does that make sense, sort of? Okay. Now, let's look at the theory of how this is going to work and what we're going to measure. So I'm going to show you a quick little video clip that really summarizes it nicely. Then I'll show you one that's a little bit more molecular so you can get a better feel. All right. So first, we show how we kind of set up the sample. In this case, they're doing multiple samples. But we put a pencil line because the pencil won't dissolve in any of these. And it'll be like a starting line for all the dyes in the mixture. And then the solvent, which is called the mobile phase, is the one that's moving. The paper is called the stationary phase. Now think about this. Each dye has a choice. It's either going to stick to the paper better, or it's going to dissolve in the liquid better. What's going to happen to it if it dissolves in the liquid better? Is it going to stay where it is, or is it going to move along with the liquid?
Stay along with the liquid.
Let's say that again. If it dissolves in the liquid better, will it stay with the liquid and move along? Or will it stick on the paper and stay where it is?
Stick on the paper. Move along. If it's dissolving in the water.
Yeah, if the liquid's moving and it goes in the liquid, won't it move with it?
Yes.
That's what I want you to see.
Exactly.
The better it sticks, the better the intermolecular force is between the liquid phase, the moving one, and the stuff you're trying to separate, the farther it's going to move up the paper with the liquid. But what if it sticks to the paper better?
And it won't move.
Then it's going to stay put. And so the way that this technique works is that the better or the closer the polarities are between the solvent, the mobile one, and the stuff you're trying to separate, the more it's going to move along the paper. And the one that does not go in the solvent very well but sticks to the paper is going to stay back. And since there's going to be a differential, they're going to separate. Do you get what I'm saying by that? Or? How about this? We're all standing together on the track, right?
Yeah.
And then a great flood comes through.
Oh,
The people whose shoes can't stick to the ground are going to get pushed along by the water. The people who have spikes can stay in the ground and stay where they are. And we're going to separate into piles based on who sticks better to the ground and who flows better with the water. Does that make sense?
So if they don't stick to the water, it'll rise.
No.
Maybe they'll stick to
The
the
ones who
paper.
don't
If they stick better to the paper, they stay where they are. If they stick better to the moving liquid, they move with the liquid. And so you can see right now already, the liquid is rising, but this isn't separating at all in the hexane. What does that tell me?
The liquid is sticky, but the thing is different.
That the mixture is stuck better to the paper, and the hexane isn't able to dissolve it and move it along.
Absorbed in the paper.
So it stays on the paper. So that's what I want you to see, the differences here between the different ones. And then we're going to show this is what the measurement that we're going to make is. You need to know these kind of measurements. So you'll notice that they're putting two samples. For our purposes, we have one mixture in each. But as the liquid rises, watch what happens. They're going to move to different degrees depending on how well they dissolve in the solvent versus how well they dissolve or stick to the paper, I should say. Now this, you can actually see the solvent line. It's called the solvent front. It's how high the liquid goes. But at some point, once we stop the chromatograms forming, we're going to mark that line as far as the solvent got. And this is the measurement you have to take. So we mark it with our pencil. And then once everything's dried up, we're going to have two lines. The starting line where we first put all the mixtures, and then the solvent front line. And then we're going to take the following measurements. So first, we get the measurement of the entire solvent front. Then we measure how far each dye left from the line, and we take a simple ratio, and that's called an RF value. So the RF distance for a given dye is going to be the ratio of how far it traveled versus how far the solvent front traveled. RF here stands for retention factor, and it's relative to the solvent. The higher the retention factor, the longer it spent time in the solvent moving. Got it? Because if it stayed with the solvent the whole way, what's the ideal number? What's the highest it could be, the retention factor? 1. Can't be more than 1 because that would mean the dye jumped over the solvent and went ahead. But if it didn't move at all, what would the retention in the solvent be? 0. And then the reason why we measure these is because if we make these chromatograms under identical conditions, we can identify unknowns. In other words, if we measured the RF of this green dye under certain conditions in a certain solvent to be 0.8, then if we measured another chromatogram under the same exact conditions and we found something that moved 0.8, we'd say, oh, it must be the same stuff. That's how this works. Now, one of the hardest parts of chromatography is finding the right solvent. Because as you can see, this very nonpolar solvent is not moving any of the dyes. Hexane is not a good one for this separation. Ethyl acetate, which is also largely nonpolar, is also having effectively no effect. Again, not a very good choice. This is acetone, and again, I'm really not seeing much movement here. It's got some polarity, but we've got almost no motion of any of the dye molecules. Ethanol is starting to show something. I don't know if you can see it from where you're sitting, but there is a bit of motion of the blue dye. It's kind of hard to see, it's barely moved, but the blue dye is about here right now. So that's starting to show some movement, and ethanol is much more polar than these other ones. But now look at what happens when I show you the water. The water, which is very polar, can you see that it's really starting to separate colors? You can clearly see the blue, right? You can clearly see the red, and I don't know, do you see in between there's almost like a little smash of yellowish green? Can you see that, or is that my imagination?
I can't wait for you. Maybe your imagination.
Okay, well, we'll let it run a little bit longer. And then this one, with the salt, you really see the blue running ahead and the red staying behind, right?
Yeah.
So this is starting to show pretty good separation. It's just a question will we catch the yellow? Because the red and the yellow are really hard separated. Now, what I'm going to do is I'm going to tell the sub, if you guys want an opportunity for a bonus, that you can try to run this lab. I'll leave the materials out there, but what I want you to do for the bonus is try to find the best combination that separates them the best. And it's just going to be kind of trial and error based on what you're learning here. Obviously, none of these relatively non-polar ones is doing me any good. But the water and the salt, if we found the right combination, maybe we could get a good combination that would be just right and separate them the best. If you can figure out that combination, that's worth 10 points. I want a clearer separation than I get with what I have here. You can figure that's up to you. It's just for fun and for the point if you want. Don't take your whole time to do it. I'm just saying it's an opportunity. Yeah.
Do you know what subject is yet?
No, I don't know for sure. Now, what I'm going to do is once these are done running, we're going to measure the RF values. And I'm going to give you this table. I'll just send it as a link. But right now, we can already start to see for the red, the yellow, and the blue, and the hexane, what are the distances it's running? 0. So I'm going to fill that in now. And that's not a surprise to me. What about for the ethyl acetate?
0.
There's effectively no movement at all of the mixture. So this is easy data. What about the acetone? Take a close look. You see any colors separating on there?
Actually, it's a bit green on the circle.
Well, that's how it looked from the beginning.
No.
Okay. So even the acetone is really showing effectively no movement. All right. What about the ethanol? This one we might have to wait. Am I crazy, or do you see some blue? You see like a bit of smear of blue up there?
Yeah, very light.
Very light. But there is some movement of the blue, so we're going to have to wait to get the official measurement on that one. And then obviously these we're going to have to wait for as well. Now, clearly the RF values, if our distances are 0, are also 0, because 0 divided by anything is also 0. Now we are going to have to measure our solvent fronts, which we'll wait for. What time do we have so far?
It is at 13 minutes.
Okay, so we'll give it another 10 minutes to run before we get the data. And while we're doing that, let me go to this second video and show you, just so you get a better visual of what's going on. But this is again about polarity and the strength of intermolecular force interactions. So beta carotene and lutein are two different substances. One of them is nonpolar, and the other one is more polar. Let's watch as this runs through its separation and make some judgment calls about the solvent and the paper that it's running through. Ready? So, what conclusion can we draw about the solvent that was used based on the way the molecules moved in their polarity?
Kind of stuck to the paper,
What did?
the polar one.
So what does that tell me about the solvent, the mobile phase? Was it polar or non-polar? What do you think? The mobile phase, the liquid that was moving through the paper. Do you expect it was polar or non-polar? Why do you say non-polar? You're right. Because the non-polar substance is the one that had the highest retention factor. It stayed with the solvent. But this one being polar didn't dissolve or mix well into that same mobile phase. So from this you should be able to draw a conclusion that we used a non-polar solvent. And that's why the non-polar one moved the most and the polar one stayed back. Does that make sense? So you should be able to match from that kind of data, or at least comment on the relative polarities of the solvent based on the solute or vice versa.
So, which one is the one all in the pure, right?
This is the salt water.
The salt water, and salt water is polar, right?
It's even more polar than pure water because it has ions in it, yes.
So how come like that has a bigger streak of color?
Well, that's a good question. The streak itself, we're going to have to kind of point to a point and say, okay, we're going to measure it from here. I usually just go to the front edge just to be consistent. The question that you're asking is good. The answer is that, basically you're asking, why is the blue dye not just staying and why is it getting left behind? I tried to make a less concentrated version of the dye, but I think this is in part because there's just so much dye in the mixture that some of it's just getting left behind. And I'm not doing this quite the right way for another reason. You see how my thing is open? Technically that allows evaporation to occur, and that's really not the way you're supposed to do this. They have special little containers that you seal so that you get a constant vapor pressure and you don't have evaporation. And I think that's also part of it. So if it's evaporating back here, it's kind of stopping the flow and it's getting dropped back. So it's not a perfect version of this experiment, but it was the easiest way for me to set it up. So yeah, I did the cheap version, sorry. But at least we're getting some kind of results here that we can measure and at least make the illustration of the point. All right, I'll leave that running a few more minutes. While that's going on, let's look at yesterday's thing and answer some questions about that. So what did you guys come up with on this? Or did you have questions you wanted to ask about it? Yeah.
On the miscibility, we got two nonpolar when we had two substances that were polar.
Let me pull that out so we can look at it again. So remember, polarity is not a yes-no question. It's a question of degree. So when you're talking about miscibility and the mixing of liquids, it's a question of preference based on relative attraction. So let's look at each one. So which one do you want to start with? The water as the solvent or the pentate?
The water.
Okay, so here's X, right? So what this is showing me is that since the green stuff is water that's been colored, that this material must be relatively nonpolar.
Compared to what?
Compared to water. And so that's why even if I stir them up, over time they reseparate. Why? Because the water molecules, when they find each other, bind to each other much more strongly based on their ability to hydrogen bond. And the nonpolar substance, right, has some intermolecular attractions even with the water. This is one of the big misconceptions students have. They think that oil and water molecules repel each other. No, they don't. They attract each other. But water attracts water more strongly than oil attracts water. So even when you mix them, they naturally get squeezed out because when the water molecules find each other, they stick much stronger than the oil or whatever can stick to the water. It would be like taking a bunch of magnets and ping pong balls and carefully mixing them in a box. And then when you shake the box, what happens?
The magnets find each other.
Yeah, they just stick because they're so much stronger at attracting each other, and they push the ping pong balls out of the way. That's what's happening here. So this is why I'm saying this is certainly less polar than the water. So we say X is relatively nonpolar. Y, you can see, is fully mixed. So that suggests that whatever is here in the water also must be relatively polar as the water. And that's why it can
So
fully...
similar polarity to water.
Yes. And then finally, with Z, we make the same argument we made with X, relatively nonpolar. And if we shake it, can you see which of these two is less polar by my shaking experiment? Watch again, ready? See how these kind of blend for a while? See how these separate really quickly? So between X and Z, who feels even less polar or more nonpolar?
Z.
I would say Z is the one that quickly separates, whereas this one kind of mixes. So that suggests to me that this one's a little bit more polar than this one. Do you see why though? Because water is very polar. So something that's very nonpolar separates from it quickly. Here, the separation is taking longer, which suggests to me that there's enough polarity in this to kind of interact with the water, but it takes more time to separate. So if I was ranking them, I would say Z is probably the least polar of all three. Y was the most polar of all three. And X was kind of in between in polarity. Yeah?
I have a question on the predicted results part. So for the, like, if you're just looking at the formula or like the thing, molecule, and you don't have it tested like in front of you, how do you know if something is, like its miscibility is like polar or non-polar?
Miscibility. Yeah, so what I'm saying there is kind of reverse engineer it. So what you did at the top was we took the measurements and made the conclusions. Now you should be able to go backwards. Based on intermolecular forces, I should then be able to predict what these ranks would be.
Okay, so like what I guessed was like if it has all three, or if it is like very polar, then it should be polar.
Yes.
And then if it's not, then it should not be. But then for like substance like X, for example, it like has some polarness, but then
Right.
it's still non-polar. So how do you
So
know?
look at the choices, because if you look at hexane, it's strictly nonpolar, right?
Yeah.
Because there's no polar groups in that
Yeah.
hydrocarbon structure.
Yeah.
If you look at the glycerin, it's very polar because of all the OH groups, because it can hydrogen bond.
Yeah.
And then if you look at ethyl acetate, it's largely nonpolar, but it's got that little polar group of oxygens in the middle. And that's why I said it's a question of degree. Very nonpolar, a little polar, super polar.
Okay.
And the ability to make hydrogen bonds, right? Now let's see if what we said about the polarity ranking makes sense when we look at the other solvent. So if I go back to X, this is now in a nonpolar solvent. Doesn't this fully mix? So it suggests that X is somewhat, or at least relatively, nonpolar, because it mixes with nonpolar really well. Look at Y. Y does not mix at all. So that suggests what? That this is very polar. Isn't that what we concluded a minute ago in the other solutions? And then this one mixes fully with Z and nonpolar, so it again shows Z is essentially nonpolar. So those two separate tests are very consistent. Now, let me pull out my chromatograms and mark the lines. And do you guys have other questions about? Any other questions about the lab we did yesterday, real quick, so I can? Here's that one. Yep, in order.
How do you find the boiling?
There's that one. How do you find the what? Well,
There are
actual
three
boiling points were
spectrums.
given, you just had to assign them.
Oh,
Number 4 of lab analysis. Yeah.
Okay, I'm gonna take some quick measurements here, and then I'll let you guys come and look at them, just so you can get a look for yourselves. All right, let me go back to the data table. And the solvent distances are as follows. Solvent front of the first one with the hexane. My original 9 centimeters for the solvent. For ethyl acetate, about 9.5 centimeters. For my acetone, 9 centimeters. All right, now it gets interesting. The ethanol solvent was about 8 centimeters. But this time we don't have all zeros. I don't see any of the red separating. I don't see any of the yellow separating. But if I look at where the blue went to, it traveled about 2 centimeters. So I got 2 centimeters of blue dye. That we can actually get an RF value for. That's non-zero. We'll get to that in a moment. Let me just keep measuring. All right, now we go to our water. About 8 centimeters of travel. And then for the colors, the red dye traveled about 6 centimeters. The yellow dye, about 6.5. Again, that's consistent with the fact that red and yellow are really hard to separate. And then the blue pretty much went all the way to the edge. So I'm going to call that 8. And then finally, in my salt water, and I'm going to send you guys this so you can put it in your lab, okay? For the salt water, it traveled about 8.5 centimeters. And, whoops. Fix that. My red only went about 1.5 centimeters. My yellow is at the edge of the red at about 2. And then my blue went up to about 8 centimeters. So I think so far it looks pretty clear to me that the salt water did the best job of separation, right? We have the biggest range. But let's calculate our actual RF values. What do I do? How do I get RF? How do I do the RF values? Hey, this is what you have to learn, so you better write this down.
Solvent distance.
This is the solvent front. So this distance is the denominator. Let's call it the distance of solvent. And then if the red was here, this distance is the distance of red. So the RF value for the red would be the distance the red traveled over the distance the solvent traveled. So the first time we can do any of that is this blue one. 2 over 8. That's it. What's 2 over 8? Oops. Isn't that 1/4? So 0.25? All right, the next one we have 3. I can't do those all in my head. 6/8 is 0.75, isn't it?
Yes.
6.5.
Oh, it's been 25 minutes.
Thank you. I'm kind of past that now. No, you're good.
You want to clarify?
I just had it in my head that it was about time. 6.5 out of 8. We get about 0.81. And finally, the last one is about 1. It's also 1 here. And then 1.5 out of 8.5, 0.18. And finally, 2 out of 8.5, 0.24. All right, so you only need this first copy. I'm going to just share it with you all right now.